Can you check if the screen is up? No.
Ivan, get your ass over here.
You're on. you're on video.
Yo, fist it up. Pre-presentation fist, bro. No.
Okay, you are Gucci.
I said.
Just start in like a minute.
Once she closes the door, we're good.
Really? Just close the door for you.
I think that what it means. No, I think she's closing it right now.
He could have gone, sat in his seat, and just stretched his arm and closed the door from his seat.
Why am I AirPods Why is there a microphone?
So, fist it out. Pre-presentation. Let's go.
Okay. Okay. Hello, everybody.
It's time. We're starting. Okay. Welcome to our presentation on simulations
And subsystem design. I'm Sharis Sen. I'm the newbie director, or I'm the director of newbie education on our team. And I'm Benjamin Goldfisher. I'm the assistant director of newbie ed. We're starting. All right. First,
why do you guys want to learn about simulating? Why is it important?
so we're gonna talk about how it's been useful for us and how it can possibly be useful for you guys as well. So first, just what is simulating? So simulations basically allows us to test robot code without having a physical robot. Okay, so that's like a simple definition. But there's actually been a lot of use cases for us on 694. So if you want to talk,
Is the stream working?
yeah, it is.
You guys didn't record, bro.
Alright, let's go to our first reason why this is awesome. Okay, research and development. So the first thing, the first way that it's helped us a lot is with research and development. So at the end of last year, after the season ended and off season started, the SE department was so excited to work on a bunch of new stuff, but we didn't have like, for example, one thing we wanted to work on was Swerve. And we wanted to get coding that right away. But there weren't Swerve modules or like a Swerve Drivetrain for like work on or test. So we decided to use simulations to test our code right away. So here's like a little bit of a sneak peek of what we're gonna be creating. You can see on the right side there's like a field with like a silly rectangle representing the robot. But that's pretty much that's kind of just like the default representation of a robot here. But you can see that it has the motion of what a Swerve bot would have. At the left, it's like the same wheel, but like also simulating the Swerve modules with tires. Okay. Oops. Okay. The second way it's been useful for us is with teaching robot code or just learning robot code yourself. So every year, 694, we get a massive amount of newbies, or at least for the software engineering department. And we found that the best way to learn robot code is through testing or like experimenting with the actual robot itself and like being able to test your code. But if you have like 50 newbies, then you can't give every single one a robot to test with. But then that also means you're not gonna have like the best experience learning. So this year we started creating simulations for that. Which is pretty cool. So we created a simulation of a Rami for the newbie. If you don't know what a Rami is, it's just a phone with two programmable wheels. So all that means is that we give newbies like a simulation of this Rami. And now with the simulation, they can test without having to without having to ask us for like roll. During build season, this is pretty much applicable to everyone. During build season, I don't know if you guys have experienced this on your team, but at least for us, oftentimes software engineering, we finish like parts and subsystems of the robot before they're actually built.
we can't really test on the robot, so we started, at least this year, we started doing simulation so we can start testing right away. Okay, I think it's time to get to the good part. Making a simulated subsystem. So, before we get to the good part. Okay, no, before we get to the good part. Alright, so, okay, we're going to talk about simulating a drivetrain. Today, so we're pretty much going to walk through the simulation process of a drivetrain. And to do that, we're first going to start off with the bare bones physical robot code that you guys are hopefully familiar with, and we'll see how that can be simulated. Okay, so the physical code, or the code for a physical robot.
We're gonna go to the code. Do you wanna go to the code? Okay, so just a quick walkthrough. Nothing like too in depth. So he's opening up the drivetrain.
Okay, so we can see we have.
Okay, at the top we have our can. Okay, so it's a drivetrain subsystem, and at the top we have our can spark maxes, the left and right motors, and then we have our differential drive, which is just the class WPI gave us to like control the drivetrain. And then in the constructor, we're pretty much just initializing the left and right motors, and initializing the drivetrain to have access to those motors. And then finally, we have a tank drive method that basically just allows us to give inputs to the left and right motors. So that's the code that we're used to. Oh wait, how do you do this? Okay. All right.
And yeah, so what we want to realize, like with this physical drivetrain, is that like what we had last time kind of follows this control flow where we have like the subsystem logic, and it gives voltages to those motors inside of tank drive, and it also reads voltages from the encoders, which we didn't directly put in there, but if you have a real subsystem like that's not simplified, you would be reading from the encoders. And what we're trying to do with the simulation is really just replace that top row of the motor and encoder with a simulation and not modify our like logic at all, so that we don't have to rewrite a subsystem just if we want to simulate it. And so this is kind of what we want to end up with, where we have like a simulated motor. It's not really a shooter sim, I just said as an example, and it's going to be able to get set to a voltage by our subsystem, and also be able to give our subsystem velocity to work with.
Talking about like more than maybe how simulations work. It's gonna be like pretty high level.
Also, it should be fine. So the way
We represent, or like the issue of simulating, of like simulations, is how do we represent physical hardware in like terms of code and numbers. So the way we do this is just we have two steps. First, we have to decide on values that can represent the hardware, and I'm going to call this state variables. And then we need to be able to calculate how these values will change when given some input. So some examples of that is just with a shooter on the right side. A value that we might want to use to represent a shooter is its velocity, how fast it's spinning. And this is like a choice that we're making because we could also decide to also keep track of how like much it's spun, how much it's spun. So but we're deciding not to do that because all we really need for a shooter is the velocity. And we're also gonna have to keep track of like have equations that keep track of like when you give voltage to a motor, you want to be able to like know how much the velocity change. And there can also be more complex examples with like a drivetrain. If you think of what like a drivetrain needs to represent, some ranges like such as position and velocity might come out, so there's like more than.
and basically
This idea of having a set of like state variables that you kind of keep track of, and some equations to keep track of those state variables. It's called the state space model. And pretty much just the idea behind that is the equations are constantly being evaluated. Like you'll see that in the code implemented later. It's like 50 times a second is being evaluated over and over, so that the state variables can be up to date.
the simulation can be up to date. So, okay. So this looks daunting at first, and you might not know the like notation behind this, but that's okay. The main idea behind this is that you can have behind the state-based model, which is just your current state, your input,
and how much their state has changed based on input. That's pretty much what this equation is representing. And the only final missing piece here is just the A and the B. So what those are just basically matrices, and in those matrices, we have a bunch of constant values, which you'll see show up in the code. We're not going to talk about how we get those constant values because you can use the libraries to find those out. But basically, the idea behind those is just they help you find how the system will develop based on
Yeah. So like in the middle here, we can see that you have the state variables for like velocity and position, and you have the input as a voltage. And so what the A and B are doing, like more specifically, is the A is saying like how should our state change based on what happened last time. So if we know the drivetrain was moving at like 10 meters per second, and we want to evaluate what happens after a second, then we would add like 10 meters to our position, and that's what's happening in A. And in B, it's just how does the voltage affect, like in this case, it would probably be your velocity. Yeah.
Is there a pointer? Can I do a pointer on this? Oh, I can. Okay. So you can see over here, if we wanted like a model, we said that our only state variable that we want to keep track of is the velocity, and you can see that in this term right here. You have the velocity, and then you have the input, both on the right-hand side, and that's evaluating to a change in velocity. So that's pretty much how you're keeping track of how the state variables are changing in your simulation. How do I turn this off?
Right, so now that we know like at a high level how these simulations should work, we're going to get on to the practical like implementation of our drivetrain. So right away, WPILR has a ton of helpful classes to simulate specific mechanisms, and the one that we're going to be using is differential drivetrain sim. And so this class can replace what we had before with our differential drive and our motors. And we'll see later, but it's going to be able to simulate the left and right side motors and give us the drivetrain's position. Yeah, so now we need to integrate it into the rest of the, man, the light just turned on, into the rest of the subsystem. And so all we need to do is set the voltages of the left and right sides of the drivetrain. So you can see in tank drive, we do sim.set inputs, and then we just have left and right voltages. And we also need to update the simulation with a time step so that it knows like when to recalculate those state variables and how much time has passed. And we have 0.02 because it's running 50 times a second. Yeah. Okay, and finally, although our simulation in the last slide did work, we have like no feedback for how the drivetrain is moving or like if it's doing what we want. And so we can add a field 2D, which basically just shows you like you might have seen at the start of the slide with the rectangle and the triangle robot. It shows you on the field where your robot is and like how it's moving around. So we can show the code real quick. I'll do a quick demo. If my laptop doesn't crash, it's completely frozen. All right. All right, so we'll wait a sec to do that. My laptop is struggling with running the stream too. I guess while we're waiting, one thing I did forget to talk about was that, oh, it's back on. Yeah, so we didn't put on the slides how you create a differential drive sim. The simulations themselves need a lot of physical constants from the robot. So you can see here we had to tell, oh shoot. We had to tell the simulation how many motors we have and what kinds. We also had to tell it what the gearing of the drivetrain was, and like the track width, which is like how far apart the wheels are, and the wheel diameter. And then we had to do this part of the top is creating like a model for the drivetrain to be created with. So these are some constants that we get from a tool called SysID from WPILib, and they're basically just telling us like how the drivetrain should behave when we give it voltage. Yeah, it's still not running. Maybe do you want to skip the demo, because this is pretty bad.
Will work. And basically, a GUI will pop up with like the
Oh. Oh wait, it might work. All right.
will pop up. And it'll pretty much be like controllable with your key.
Any day now. Oh my god. Alright. Okay, so you can see with the field down here, it just represents like this big rectangle that the robot can drive around in. And I'll move it more onto the field. So right now I'm controlling it with my keyboard. And you can, oh geez, there's so much lag. It's gone. Alright, it's back. Yeah, so we have the robot and we're moving it around with our drivetrain, just controlling the left and right tank drive. And yeah, so right now in this state, like you could try and run some autons or like just do testing with the drivetrain. But we're gonna do some more. Alright, so we're gonna go more in depth with this. So what if you wanted to have physical and simulated mechanisms at the same time? Like, let's say if you have what Shari was talking about before during build season, if you want to simulate the physical code that you've already written. Currently, if you want to do that and like separate them into different classes, in all of the commands that use your drivetrain, you'd have to like replace it with a simulated version or the real version whenever you want to switch. But we can fix this. There's a better option. So if we create an IDrivetrain, this is just like a name that we came up with, like a yeah, it doesn't really matter. But as long as the sim drivetrain and the physical drivetrain both extend this class, so they both, like you can see here, we have an iDrivetrain and it has a tank drive that both the sim and the real drivetrain need to implement. So as long as both have that method, then we can use them in commands without caring if it's simulated or not. So you can see in our like drive command down here, we have a drivetrain and we're also using tank drive on it. And you can see this is the differences between the sim drivetrain and drivetrain, where they both extend iDrivetrain and they both implement tank drive, but they work differently internally. Alright, so that's pretty much it for our drivetrain. We're going to go over some special cases, like an elevator. So elevators are like the only case where you have to simulate gravity, and WPILib makes a special class for you, which will do that. And it's pretty much the same structure as your drivetrain, where we have a sim, we set the input voltage of the simulation, and we update it. And there's also other classes like a flywheel sim and things like that, that you have to, like, depending on which mechanism you're simulating, you just have to look at which one fits the best. Alright. So with an elevator, we can't really use a field 2D to see how high it is, because it doesn't give you back a position. It's not moving around on a field. But we can get some feedback visually by using a mechanism 2D. And this is another class that WPI has made so that you can see how tall the elevator is right now. And all we have to do for this is just in periodic set the height of your elevator, and yeah, that's pretty much it. All right. So yes. So any questions? I guess.
Can you go over the inheritance one more time? Like,
Yeah,
does the
sure.
simulated drivetrain and the real drivetrain both extend from iDrivetrain?
Yeah, I can show you in the code, but they both extend from iDrivetrain, and oh jeez, it's so slow. Yeah, but iDrivetrain in here, it has a tank drive, so that the commands can call tank drive on it, but the sim drivetrain and jeez. Yeah, but the sim drivetrain here, and this is the real drivetrain, it extends iDrivetrain, and it also implements tank drive down here. Yeah. And we just decided to do it this way because it's like more organized. If we try to put both simulated and physical stuff in the same class, it gets pretty cluttered pretty fast.
Do you simulate a swerve drive?
So a swerve drive is much more complicated, and you can't use a differential drive sim like we did here. The way that we went about it is we used a bunch of we simulated a bunch of individual motors using a more using the flywheel sims that we talked about. So for example, you could simulate the drive motor and the turn motor separately using flywheel sim, and put those together into a full swerve drive. I don't think my laptop can handle opening the swerve code, but you can take my word for it.
Can you make a shooter simulation?
Sure. Let's live code a shooter simulation.
It's been half an hour. So yeah, make the interface. Yo, this guy's.
Okay, so we're gonna try and do like an example shooter subsystem. So let's do the eye shooter. And in commands, the way that we'd want to control this shooter is probably by setting its RPM. So we're gonna make this a subsystem. Oh, jeez. And we're gonna make a method that'll set an RPM.
What does abstract mean?
Sorry, honestly. Alright, so pretty much it just means that like the shooter and the sim shooter that extend from this, they have to implement like all of the abstract methods in here. So if I say abstract void and then let's say like set target RPM. Alright. Okay, cool. So all of the methods are, sorry, yes.
If in a like a shooter command, you needed to check if it's like at the target RPM, so you need like the current RPM. Could you add those as methods to this as well?
We can also do that. So we can also get the current RPM from a shooter. So we can add another method for that. I guess we'll call it get RPM. Okay. Alright, so I think our eye shooter looks good right now. Let's try and make simulated shooter. Alright, so first off, we're gonna want to use the flywheel stem that we talked about before, because we don't need to keep track of the position of the shooter, we just need to keep track of its velocity. So we have to make it extend iShooter. Alright, and then we'll add a flywheel sim in here. Okay, cool. Yes, I did. Alright. And then we're also going to create this flywheel sim. Yeah, I'll do it later. Okay. I don't remember. Alright. Alright. So there are a bunch of different constructors for flywheel sim. I think we're gonna use... Oh god. Damn. This is so painful. Okay. So it wants a plant, or like a model of a system with only one state, or with only the velocity. And WPIlib also has a class called Linear System ID, which you might use a lot if you want to create these simulated motors. And they can create these like models of motors from like a bunch of different kinds of input, yeah.
This simulation thing is gonna use the like A and B equation from before to do like.
Yeah. So this, what we're gonna do right now is basically going to create those A and B's that we saw before, and it'll like set up the equations that we can use it later on.
Is this gonna set up the A and B for like, the flywheel, or just the motor that's controlling the flywheel?
It's just gonna, it sets it up for the whole system. So it's going to like, because the motor, like the hardware that the motor is connected to also affects how it's going to react to like voltage and stuff like that. Yeah.
Yo, how do you guys keep all this organized? Because now instead of having like one shooter subsystem file, you have 3. Where do you put all this?
Well, the way that we did it in most of our projects, we have like an iShooter in your subsystems folder. We have like a shooter folder, and then you have your like sim shooter and your like real shooter in there. And like one downside to this is that you also, like if you want to make changes to your sim shooter, you also probably want to do that to your normal shooter, but it keeps it more organized. Yeah. Oh, that's just as like a convenience, so that we don't have to do in here. If we didn't do that, we would have to do like extends iShooter, extends subsystem base, and it's just like wait, is that even the syntax in Java? I don't know.
Like iShooter.
Yeah.
If you want to pass iShooter as a requirement to a command, it has to be a subsystem. That's why.
This guy's right. Random audience member is also right. But if you want to use this in commands, it also has to be a subsystem. So yeah, no, because the commands, like we showed on the slides back here, the commands actually store the IDrivetrain. So if you want to do, like, you know how in commands, when you create it, you have to add all of the required subsystems. So if you want to add your drivetrain as a requirement, your iDrivetrain has to be a subsystem. Yeah. Wait. Wait. Can you like elaborate? Wait. What do you? So you're saying like it could be an interface that extends. Yeah, I think that might also work. Yeah.
There was networking stuff in subsystem base that I didn't want to figure out what it did, so I just ignored it.
Yeah. All right. So we're gonna keep on going. Linear system ID. Jeez. All right. So this is a velocity system because it only has the only state that we're storing inside is a velocity of the shooter. So we're going to use identify velocity system, and we're going to use these values from the sysid. So I'll just put in random numbers for now, but
So it's like basically what I was saying earlier. And, they can calculate for us, and that's what this idea is.
yeah. And then so the next argument is like which motors are in your shooter, and so we're just gonna assume for this one, let's say we have two like neos. So the way that we do that is DC motor get neo, and then we can say two motors, and that's our gearbox. And then our gearing, just for simplicity, we'll do like 1-to-1, which is yeah, just one. Okay. Okay, so next up, I think we want to implement the methods from iShooter. So we're going to want to set a target RPM. So I think in our subsystem, we should probably store a target RPM so that we can know what RPM we want to reach. So we're just going to do target RPM, and then inside of our set target RPM, we'll just set that variable. Alright. Okay, and then next up, we also want to be able to get the RPM from the flywheel. And the flywheel is very helpful. It already has these methods for us. So we can just say, oh, we have to write the method first. So syn get RPM. Sorry, that's a double. Alright, and then we're going to want to return sim get angular velocity RPM. It's going to work out for us. Alright, so last, we just need to set the inputs of this subsystem, or of the flywheel. We're also going to need a controller for that, because we need to reach this target RPM based on what RPM we have now. And I think PID is probably something most of you guys know. So we're going to store a PID controller and use that in periodic, or we'll do simulation periodic. It doesn't really matter in this case because this class should only be run when it's in simulation, but we'll use simulation periodic. And so we're going to set the input set input voltage to controller Alright, and then we're going to calculate based on the measurement, which is our simulation's current RPM, so we can just do get RPM, and set point, which is target RPM. And last, we just need to update this so that it can do the calculations for our new state, and that's pretty much our shooter. I just have to fix import stuff, and that's pretty much it. So any questions like after the quick example of a shooter simulation? Yeah.
Could you use the simulation to calculate like I guess how far the ball will go depending on depending on the voltage?
You would have to use some more complicated like math for that because the shooter, like, although you know what RPM it's running at, there might be more factors for how fast the ball gets accelerated based on that. But if you know how your ball like reacts to the RPM, then you could probably do like a projectile motion like equation or something and see how far it goes. Yeah.
Can you explain how you use this throughout the build? Something you're planning your sims from the beginning, or is it you kind of wait until you have structure and you throw it later?
So in the beginning, at least with last season, we started with our physical code, so like knowing what hardware we're going to put into it and like what general commands we're going to want. And then after like we're pretty set on those, we can start writing our simulation code. And because the logic of it should be the same for physical and simulated, then we can just